Hello everyone and welcome to the PCD of CodeChef Starters 192. Today we're going to discuss problems A, B, C, and D. Okay, so the first four problems. Let's get right into it. Okay, problem A. All right, so the question is security lines, and it says that there are n security queues numbered from 1 to n. Initially, there are A of I people standing in the ith queue. Initially, there are A of I people standing in the ith queue. You are the last person in the first queue. All right. So you're the last person in the queue number one. Every second, the following happens. You will either stay in the same queue or move to an adjacent queue. That is, if you're at QI at the start, you can stay at QI or move to QI minus one. All right. If you move to a new queue, you will be the last person in it. Then the first person in every queue will complete the security check and leave. Naturally, you'd like to finish your security check as soon as possible. What's the minimum number of seconds you'll need if you act optimally? All right. And n goes up to 500, t goes up to 500. So even n squared solutions would pass, although a direct O of nx solution exists. So let's have a look at the solution. It was the simplest problem, so I expect most people would have solved it and they wouldn't want me to spend too much time on it. Okay. So let's take the first example. The first queue has 5 people, second queue has 2 people, third queue has only 1 person, and fourth queue has again 3 people. All right. So I know that I am the last person in queue number one, correct? So therefore, if I choose to stay in queue number one, if I stay in queue number one, then it will just take me 5 seconds, right? So if I stay in queue number one, it will take me A of 0 seconds. Okay. So this is what happens if you stay in the queue and you don't change the queue. All right. Now, what if I decide to, I'm at this queue and I can move to any adjacent queue, right? So I can move to the next queue. And since there's no previous queue there, I can't go backwards, but I can move to the next queue, right? And if I'm at some queue over here, then I can go front or back, right? I can move to adjacent queues. So let's say I'm at this queue and in 1 second, I can move here, right? So what happens in 1 second? Well, in 1 second, the value decreases by 1, right? So there's 1 person over here, but I am a new person who just arrived, right? I am a new person who just arrived to this queue. So it actually becomes 2. All right. Now, what happens if we go to, let's say, the third queue? Okay. So in the first second, this becomes 0, right? But we're still here. Then in the second, we reach here, right? But then we are the only person in the queue. So then it takes total 3 seconds, right? Right. So no, wait. So in the first second, we reach here. In the second, we reach here. And then what happens? There's 0 people here, right? So we can just go directly, I guess, in the second. Right. So that's why the answer for this case is 2, right? Because the best way we can do it is to go from here to here and then here to here. That's what the example is described. We move to the second queue and now the counts become 4, 3, 1, 3. We move to the third queue and then the counts become 3, 1, 1, 2, right? And then we were the first person in the third queue. So we can simply just leave, right? Okay. So how do we write for when we are not in the queue? So how do we write for, like, what is the answer if we do not stay in queue number one? So let's say we exit from queue number I. We exit from queue number I. Okay. Then obviously it will take I seconds to get there, right? So let's say if we are starting at this position and this position is I, then it's going to take I seconds to reach here, correct? It's going to take I seconds to reach here. Now, if by now the queue is already 0, then we can simply escape, correct? If by now the queue is already 0, then we can simply escape. So in that case, the answer will simply be I. But what if the queue is not 0? What if the queue is 2 or something like that? Then in that case, you can show that since this much time we have taken to reach here, right? So this much is I time we have taken to reach here. In that much time, it has decreased by 2 minus I, correct? So basically what has happened is, whatever the original value of A of I was, our answer will be A of I plus 1, okay? Our answer will be A of I plus 1. So there are two cases. Either it became 0, then our answer is simply the time taken to reach there. Otherwise, the answer is x plus 1, where x is the time that it takes to finish this. So I'll give you an example. Let's say we have an array 100, 100, 7. All right. So we stay here, then our cost will be 100. If we move here, our cost is going to be 101. And if we move here, our cost will be 8, or our time taken will be 8. And why will it be 8? Well, let's say we move here in 1 second, then this becomes 6, right? Then again we move here, and it's 2 seconds now. And then this becomes 5. But because we are here, because we are a new person in the queue, right? The queue has increased by 1. The queue has increased by 1 because we are a new person over here. So that's why the queue remains 6. So basically 2 seconds passed and the queue has remained 6. So the total time will be 8, or the total time will be x plus 1. All right. So basically, since we take I seconds to reach, in that much time, x has decreased by x minus I, but our time taken also will be counted here. And then because we are a new person in the queue is not empty already, there'll be a plus 1. So therefore, the answer will be minimum of I and x plus 1 for this case. Sorry, not minimum. It will be maximum of I and x plus 1. Because if x is larger than I, then we'll reach there first. Otherwise, if x is smaller than I, then it will become 0. So as soon as we reach, we can pass out, right? We can pass out of the queue. So that's why the answer will be max of I and x plus 1. So yeah, here also it should be max. Sorry about that. Right? So how do we code this up? We can have a simple O of n code. Okay. We go of n code. Our answer will be A of 0. And then for I from 1 to n, okay, our answer will be updated to minimum of whatever the current value of answer was, and max of I and A of I plus 1. Okay. So this is the full code for it. And we can do this in big O of n. Someone has a doubt in the chat. Sai K, if you do not have a question, can you please mute yourself? Because this is also being recorded for later. Okay. Aditya asks, if array minus I is less than equal to 0, then the answer is minimum of answer and I. Otherwise, the answer is minimum of answer array I plus 1. Huh. I think that should be correct, right? That is almost exactly what I described right now. In what case can it differ? Okay. Yeah, it should be less than 0, not less than equal to 0. Because if it is just now become equal to 0, then you would be an additional person in the queue. I'll show you an example where yours fails. So if you write it that way, this part should be less than 0, not less than or equal to 0. And I can show you why. So for example, we have a case like this, 100, 100, and 2. Okay. So what happens? Let's say we have to move here and exit. Okay. So in 1 second, what happens is we get 99 and 100 and 1, right? Because we jumped from here to here. Now in the second, what happens? We jump from here to here, right? So this becomes 98. So here one person leaves and then we also leave. So this also becomes 98. And then here, this becomes 1. It does not become 0. See, it does not become 0 already. We still need to wait a little more for this to become 0, right? Because that person has not left yet, right? He's still going to leave. So when we add to the queue, we become 2, then he leaves. So that's why this will remain 1. And then in the 3rd second only, we get to leave, right? In the 3rd second only, we get to leave. So your answer is off by 1, right? So yeah, it's a little subtle question. So I can just write the correct code as well. So the correct code for this will be like this. I've written in the chat. Yeah. So only in the case where it was already 0, right? In that case, we can directly leave because we have reached there and we can directly get out. But in this case, when it is equal to I, array of I is equal to I, then while the other guy is leaving, we're still standing. Because if you observe in the question, first we move, right? First we move, then the first person leaves, right? It's not like the first person leaves and then we can move there and leave. So that's why your answer was off by 1. It's the same idea, but yeah, small mistake, I guess. All right. So I think this question was understandable. The time complexity is obviously big O of n, since we're only doing one loop, right? Time complexity is big O of n. And I'll quickly show the implementation and then we can move on to the second question, right? Okay, so the implementation of this question is here. I didn't even store in an array. I just wrote answer is int max. And then I took minimum of x and I, sorry, maximum of x and I. And yeah, so what I simply did was the first element, right? The first element will be, so in the first element, we just take its value directly, right? So that's why I added I greater than 0. So for the first element, this will simply be max of x and I. And for all other elements, it will be max of x plus 1 and I, which is exactly what we want. And then I print out the answer. So that's it for the first question. Let's move on and solve the second question. The second question is no 3, please. How many people got the second question in this contest? I think it was a bit tricky, at least for me. And so the code I wrote in the contest was not the best code. Okay. So I will explain both methods. I found a better method after the contest. I'll explain that first. Then I'll explain my method and I'll explain the code for both methods. Okay. So question 2. Okay. For an array B of length n, we have the following. The prefix sum array of B is an array P. Okay, so we know what prefix sum means. So it's just prefix sum array. B is called good if every element of its prefix sum is not a multiple of 3. Okay, so it should never, the prefix sum should never leave a remainder of 0 with 3. Okay. For example, B1121 is a good array because its prefix sum is 1, 2, 4, 5, and none of them are multiples of 3. But 1122 is not a good array because its prefix sum is 1, 2, 4, 6, and 6 is a multiple of 3. Okay. You are given an array A of length n. Every element of A is either 1 or 2. At most once, you can reverse a prefix of A. That means you can take any prefix, right? So if this is an array and we have something like this, right? So you can consider this as a prefix or this as a prefix, and we can reverse the elements in the prefix. Okay, so this 122 will become 221 and so on. Okay. Is it possible to make A good? Okay. Is it possible to make A good? What does good mean again? Good means that there should be no multiple of 3 in the prefix sums. Okay. And also we should see the constraints. So n goes up to 10 to the 5. So we need a n or n log n solution. And A of I is only 1 or 2. So pay attention, a of I is only 1 or 2, which does not change that much, but yeah, it simplifies the problem a little bit. Okay. It leads to some solutions which otherwise might not exist, but yeah, a of I is only 1 or 2. Okay. So, right. Let us take some examples and see what the question is asking and how to approach it. So let's take the first example is already good, so we don't want to see it. Let's take example number 3, I think, right? So we have 1, 2, 2, 2, 1. Okay. Let us compute the prefix for this. Okay. Let us compute the prefix for this. And first thing to keep in mind is when we are computing the prefix, we will take mod of 3. Okay. So we'll compute the prefix while taking mod of 3. Okay. That makes sense? Yeah. Okay, so we'll take the prefix with mod of 3. And why is that? Because we simply need to check if it's 0 or not. And we can know if it's good or not. Okay, because the numbers themselves don't matter. Only mod of 3 matters. Okay, so we get this as 1. We get this as 0. So already it's violated, right? And then if we add 2 to 0, we get 2 again. Add another 2, we get 1. So this is all the prefixes mod 3. Okay, prefixes mod 3. Prefixes mod 3. Okay, to make sure that we understand that we're taking the prefix mod. So we can see that there's a violation here, right? Now if we just reverse this, nothing is going to happen because it will become 0 and 1, right? So there's no point reversing this. I mean, like, sorry, if we just reverse this, it's going to become 2 and 1, right? But the 0 over here will not change, right? Because the sum remains 3. So the sum will remain the same. So basically, we need to reverse some point after the last 0. Okay. So the first intuition, which we get directly from the example itself, even before solving the example, you can get this intuition, is that our point of reversal must occur after the last 0, after the last 0 in the prefix array, And by last 0, I mean the last element, which is divided by 3. Because if we reverse anything before, it will not change the 0 over here, right? And if we reverse this only, then again, there will still remain a 0 over here. So the only things which can change are either reversing like this, or reversing the whole array, right? Those are the only things which will change the answer. Okay. So keep this first intuition in mind. All right. Let us try some ideas and try to see how to reverse it. So we have 1, 0, 2, 1 and 2. Okay. So then how to let's try reversing this, right? So this was our first option to reverse. What happens? So in the original array, the numbers were 1, 2, 2, right? So here what will happen to the numbers? Here the numbers will become 2, 2, 1. Right. So this is the prefixes. This is the array. So if we reverse this portion, it becomes 2, 2, 1, 1, 2. Right. And notice that since the sum over here does not change, these prefixes will remain the same, right? These prefixes will remain the same after or before reverse. Right. So we don't need to worry about that going wrong, right? We only need to worry about the prefix which we have reversed. Now, what is the new prefix array? New P. So here there is 2, right? The next 2 plus 2 is 4, right? 4 is 1 more 3. So we get 1 over here. Then you add 1. So 1 plus 1 is 2. 2 more 3 is 2. So we got 2. After this, it will remain the same, right? So we can just stop here, right? Right. So this is the new values of the prefix over here, right? Observe in the question. They have explained this example as well. So yeah, The array A, by the way, was 2 over here. Sorry about that. I believe the array A was 2. Yeah. Okay. Yeah. So this is what we obtain. Right. So this is a new prefix array. Sorry, 1, 2. Right. This is a new prefix array. And as you observe, we have lost the 0, right? There's no 0 anymore. No 0 anymore after the reversal, right? So we have successfully removed the 0. But how can we be sure that we will remove the 0 or not? And that's what we aim to find, right? So let us try some more examples, okay? Let's try another example. And we have, let's say in this example, we have 2, 2, 1, 1, 1, 2, 1, 2. Okay, I just took any example because if we're solving constructive problems, generally we should try a bunch of examples and see. So what is the prefix array for this? We get 2. 2 plus 2 is 4, which is 1, right? Then this will be 1, this will be 2. This will be a 0, right? This will be a 1. This will again be a 0. And this is mod 3 again. This will be 1 and this will be 0, right? So now here we have a 0 at the last position, right? That means that no matter what we reverse, the sum of the whole array will be divisible by 3, right? So if the last position is 0, obviously we cannot have an answer. And as we observed earlier, our point of reversal must occur on the left of the last, on the right of the last 0, after the last 0 in the prefix, right? So that's why, so the answer will simply be -1, okay? No, Rohit, we're getting to that point. We have not discussed it yet. What I'm saying is basically we can only reverse it after the point of last 0. So I think that much you should understand, right? Okay. Now let's try to see another example and see what happens. Let's say I have a very similar example. Okay. Okay. Now the prefix array for this will be 2, 1, 2, 0, 1, 0, 1, and 2. All right. Now the question is, can we reverse the elements here? Okay. Now the question is, can we reverse the elements here and see if our answer matches or not, right? So can we reverse the elements here and see if our answer matches or not? And for this, let us just write the elements in reverse and see what happens, right? So let us write these elements in reverse. So new array will be, our new array will be 2, 2, sorry, 1, 2, 1, 1, 1, 2, 2. And finally, this one is not reversed. So it will be like this. And what will be the new prefix? New prefix. We are trying an example right now. Okay, guys. Trying an example. We're trying to figure out how to solve the problem. Okay. Okay. So the new prefix will become 1, 0. So already it became 0. So this is an invalid way of doing it. Okay. And similarly, if you try to reverse this whole thing also, you will see that 2 and 1 will form a 0. So the answer is -1 for this case. Okay. So how do we distinguish between the two cases? Okay. Or the answer is no for this case. All right. Yeah. So how do we distinguish between the two cases? How to approach this? All right. Okay. So here's the ideal way, and I think I'll explain this method only, which is, I think, very simple to understand. So let's say this is our point of last 0. Okay. This is our point of last 0. Okay. And let's say this is some I, and we choose to reverse from this element I. Okay, we chose to reverse from this element I. Now these prefixes will stay the same. Okay, so this is the prefix array. This is the prefix array, and these prefixes will remain the same. These prefixes will remain the same. Will remain same. Okay, so we only need to care about what happens to these prefixes, right? And if you observe, let's say the prefix at this position, right? The prefix at this position is some value. Then let me call this P of I plus 1. Okay. Then okay, so let's think about it like this, all right? So I'm choosing to reverse from this position I from 0 to I, right? So I can reverse a prefix. So I can reverse from 0 till this position. So this is not a value, this is a position, right? So I'll write it like this. I can say that this is the ith position, and I decided to reverse over here. So what will be the value over here? Okay, so what will be the value over here once I have reversed it? So once I reverse this value goes over here, right? This value goes over here, and then this value comes over here. But what will be the new prefix value here, right? What will be the new prefix value here? Okay, and I can show that, we can show that the new prefix value at some position j, right? The new prefix value at some position j will be prefix of j minus prefix of I. Okay, so it will be prefix of j minus prefix of I. Yeah. So if it was like, let's say 1, 2, right? So here it will be 1, 2. Here the value will become 1 itself, and here it will become 0, right? So it will be prefix of j minus prefix of I mod 3. Okay. And this is our key idea for this problem. This is our key idea for this problem. And it is like very necessary that you understand that. Okay. So I can show you some examples until you get it. But yeah, the key idea is when we reverse some prefix over here, then the new values can be gotten using prefix of j minus prefix of I mod 3. And let me just show you an example. Okay, so I have an array 1 2 2 2 1 2. Okay, and I reverse it, or maybe I'll write a simple array so it's easy to understand. Let's say I have an array 1 2 2 1. Okay, now if I reverse it, I get the array. Okay, so the reverse will be the same here. Let's say I have an array 1 2 2 2, and I reverse it, I get an array 2 2 2 1. Okay, now let us take the prefix values. Okay, so the prefix is 1 here, the prefix is 0 here, the prefix is 2 here, and the prefix is 1 here, right? Similarly, the prefix values over here will be 2 1 0 1, right? Now let's say when I was reversing this, right? So the first value I can be sure is a 2, right? Because it's simply the same value itself. And the second value, the value which comes here, right? It's going to be this prefix. So prefix at this position j, right? So this is the second value of this array. It will be prefix of j minus prefix of I, right? Mod 3. Okay, so prefix of j was 2, prefix of I is 1, and we take mod 3 and we get 1, right? 2 minus 1 mod 3 is 1. And observe carefully that why this is happening. This is because when we have done the reversal, then this value is simply the sum of these two mod 3, right? And in the original array, it will be the sum of these two mod 3. And if we want the sum of these two mod 3, then we can simply take basically, if we want the sum of these two mod 3, then it's the sum which occurs over here, right? So it's prefix of I minus prefix of j. Either way, you want to write it. Mod 3. Does that make sense? If it doesn't make sense, I'll explain again, guys. Just put it on the chat. Basically, what I'm saying is, when I do the reversal at some position I, right? At some position I do the reversal. Then if I have an element over here, what when it goes and becomes reversed, what is its new prefix value, right? And its new prefix value will simply be the sum over here, mod 3, right? And if I want the value of sum over here, mod 3, then that is simply prefix at I minus prefix at j, right? So prefix at I minus the prefix at j. So this, I'll get this whole thing, right? Mod 3. Does that make sense? And so when will it be 0? So when will any element make 0? Element becomes 0, right? That will only happen if prefix of I equal to prefix of j. Okay. So basically, we have to ensure that if we are doing a reversal at some position, if we do our reversal at some position I, which is after the last 0 occurrence, of course, which is after the last 0, then there should be no value. There should be no value j less than I, such that prefix of j is equal to prefix of I. Okay. So this is the key idea. Basically, if there is ever a value of prefix of j equal to prefix of I, then what happens is when we reverse this, right? When we reverse this, and let's say here prefix of j is 2. Here prefix of I is also 2 at this position. Okay. So when we reverse this sum over here, it becomes 0 mod 3, right? Because here there was a 2, here there was a 2. So this whole sum is a 0 mod 3. That's why when we reverse it, we get a new 0. Does that make sense? Basically, if we reverse this and this was a 2 and this was a 2, then everything in between must have been a 0 mod 3, right? Because 2 plus x mod 3 equals 2. So x must have been 0 mod 3, right? So if we reverse in a case where there was an element equal to our current value of the prefix, then it's not possible. Like then there'll be a 0. So it won't be possible, right? So we have to do a reversal at some position I. Then there should be no value such that prefix of j equals to prefix of I. Okay. And this approach is big O of n. And I can quickly write the pseudocode for this. So pseudocode. Okay. So first, for each I from 0 to n, calculate value of prefix of I, right? How do we do this? We can simply take the input and do prefix of I equals prefix of I minus 1. Prefix of I minus 1 plus A of I mod 3. Okay. So this is how we calculate the values of prefix. And then we can have a position for number of occurrences of 0 mod 3, number of occurrences of 1 mod 3, and number of occurrences of 2 mod 3. Okay, so it will be something like vector int counts or something like that, and initially it will be 0 0 0. Okay, and we also find the last occurrence of a we also find the last occurrence of 0. Okay, so if the value of if prefix equals 0, then we can update the last occurrence, right? Update last occurrence. Okay, now what we need to do is for I from 0 till n, right? So obviously we can update count of prefix of I will be increased because now we have a new prefix of I, and also if I is greater than last occurrence, so it's possible to fix it, right? If I is greater than last occurrence, if count of uh, prefix of I is 0, right? If that value had never occurred before, if that value modulo 3 had never occurred before, then the answer becomes true. Okay, so this is our final pseudocode for this question. All right. Any doubts? Like, does that make sense? Actually, the method which I implemented during the contest was a bit unnecessarily complicated. So I'll just quickly implement this method right in front of you guys and show it to you. I think the method I implemented in contest, like I'll give the link to the submission, but I don't think discussing it will be very helpful. So yeah, I'll just quickly implement the code for this. Okay. So our vector v, right? It stores the values of v of I, right? And our vector p will store the values of prefix. Okay. And so p of I will be equal to sum here. Okay. So sum is the value. Sum is the value which is storing the prefix till some position, right? Now we can make a vector count of size 3 and 0, right? Okay. And what we can have is right. So this should be the code for this question. All right. Let's just quickly run it on the samples so we can see that it passes all the samples, right? Right. Okay, so right now the contest is, oh, I think I need to submit it using like the problem link or something like that. Yeah, submit in practice. Yeah, as you can see, it passes all the test cases. So this code was valid. All right. So quickly go through the code. If there are any doubts, please ask. So basically what I'm saying is I calculate the vector and I calculate my prefix sum. And then I also find the place where my last zero occurs. If there is no zero in the entire array, then obviously I can print yes because there's no multiple of 3. Otherwise, I assume my answer to be false. I have a count of the occurrences of 0, 1, and 2 in my array, right? In my prefix array. If I am above my last z, then I can check if the count of the current value of the prefix is 0, in which case I know that at the current point I can reverse and my answer becomes true. Uh, Otherwise, if there's no such point, then my answer will remain false. Okay. And here I'm increasing the count of the prefix value. Any doubts? I didn't understand, Rakesh, what you're talking about. Basically, our solution, our entire idea hinges upon this. Basically, our entire idea hinges upon this expression. Since every reversed value takes one of these values, right? And we don't want this to be 0. We don't want this to be 0. So whatever our current prefix of j is, we don't want whatever our current prefix of I is, we don't want a prefix of j before that with the same value. So that is our idea. And the time complexity for this idea is big O of n. And complexity is big O of n. So like I thought of this after the contest. My original solution was much worse. So I think it's best we don't discuss that because it's unnecessarily complicated and in the end it uses the same idea only. All right, let's move on to the next question. I think this is the best way to solve this problem. If you have any better way, do put it in the chat. Okay. Moving on to question 3. Equate xy. Okay, so I don't know, but I thought this was a particularly interesting problem to solve for me. Equate xy. Question 3. Okay. You have with you 4 positive integers x, y, z, and c. You'd like to make x equal to y. To do that, you can perform 2 operations. Pay 1 coin and either increase or decrease z by 1. Okay. So z can never become 0. It will always be some positive integer. And you can increase or decrease z by 1. Otherwise, you can pay c coins and do one of the following. Replace x with LCM of x and z and y with LCM of y and z. Otherwise, replace x with LCM of x and z and y with GCD of y and z. So basically the similar operations. The operations can be performed how many ever times you like and in any order. Find the minimum number of coins you need to pay to make x and y equal. It can be proved that it's always possible to make them equal. Okay. And x, y, z, and c go up to 10 to the power 9, right? So we cannot use very high time complexity for this, right? And there are 1,000 test cases. Okay. So how do we approach this? All right. So basically our question says, we are given a x, y, z, and c. Our target is that we want x equal to y, right? So this is our target. Okay. And what are we allowed to do? So we are allowed to change x. We can change x to GCD of x and z, right? And y can become LCM of y and z, right? Or y can become GCD of, sorry, x can become LCM of x and z, and y will become GCD of y and z. Okay, so these are our 2 allowed operations. And the other operation, so these 2 operations cost c coins, right? These will cost c coins. And this is the first operation allowed. The second operation is simply z, we can increase or decrease by 1. Increase or decrease by 1. And this costs 1 coin. Okay, so this costs 1 coin. Okay. So now this is a very observation and math-based problem. So I will not show many examples, but I will just show you the observations directly. Okay. So obviously the way you solve this in contest is you write down a lot of examples and you try to see what works. So like one thing you can know from your math maybe is, so let me just write it down. First intuition or intuition one. Okay. If we let Z be the same, okay, let Z be the same, okay, then observe that GCD of X with Z, okay, then we take LCM of this value with Z, okay. So it's like we perform the operation twice, right? And this value will always equal to Z, okay. If we take GCD of a number with Z and then we take LCM with Z, then the value will remain Z itself. Okay, so this is our first observation, right? And why is this true? Imagine X was, let's say, 10 and Z was, let's say, 7. Okay, then GCD of 10 and 7 will be 1, right? Because they have no common factors, the GCD will be 1. Then we take LCM of that with Z. So LCM of that with 7 will be 7 itself. And why is this true in general? Well, it's true in general because let's say GCD of X and Z is G. Okay, so then X equals G times K1, right? And Z equals G times K2. Okay, so when we take the GCD of both of them, we get G, and then we take LCM of G with G times K2, right? So it's like basic maths, I think. If you take LCM of G with G times K2, then obviously we'll get G times K2. Since this factor is there in both, right? And this is the new factor, so this will be the LCM, right? So this is the first observation you should make, that GCD of a number, like first we take GCD with Z, then we take LCM with that with Z, and it will give us Z back. Okay. Now the very related thing is that GCD of LCM of X and Z with Z, this is also equal to Z itself. Okay. So these two are our key ideas. If we take LCM then GCD, or if we take GCD then LCM, we get the value Z itself. And how do we do that? Observe this also. So if again we use the same argument, okay, let's say X was some G times K1 and Y was some G times K2, okay, then what will their LCM become? Their LCM will simply become G times K1 times K2, okay. Here G is the GCD of X and Z. Here G is the GCD of X and Z. So this will be the LCM, okay. Now if we take GCD of this with G times K1, we will get back obviously G times K1. So we'll get back Z. So if we take LCM then GCD, or if we take GCD then LCM, then we get the same value of Z back. Okay. No matter whatever the starting number is, whether it is X or Y, right? Right. So this should be our first intuition. And what does this mean? This means that if you take any example of A, B, C, D, if you have A equals 10, B equals 20, C equals, let's say Z equals, Z can be anything, okay? Z does not matter here. Let's say Z is 7 and C is 2, right? So we simply need to do two operations. First take GCD of this two, right? GCD of A with Z and LCM of B with Z, right? Then we do the opposition in reverse. So we can take LCM of this value and, right? Then we can take GCD of B with GCD of LCM of BZ with Z, right? So when we do the operations, first we do the first type of operation, then the reverse type of operation, and both values become Z, right? So both values have become equal, right? Values of both X and Y have become equal. So it should not be A and B. In the question, it's X and Y. Sorry about that. But yeah, observe that both the values have become equal in simply two steps. Okay. So basically, our answer will never exceed two steps of this. Okay. Our answer will never exceed two steps. So first observation. So from this observation itself, we can always make it equal x and y equal, okay, by using the second operation at most twice. Using second operation at most twice. First we use it with GCD LCM on x and y. Then we use LCM GCD on x and y. Okay. So using second operation at most twice. Okay. So the maximum answer is 2 times C. Okay. Maximum answer is 2 times C. Okay. Now this is, you can call it intuition 1, right? Now the second intuition is, so this should be very obvious. If x equal to y, then answer is 0 and we can just leave it. Okay. Answer is 0. Okay. And third idea is, let's say if x is not equal to y, right? If x is, and this is the interesting case, then we can let x be the smaller one, okay? Because x and y does not really matter. So if y is smaller than x, we can just swap the values. So let x be less than y. Okay. If it's not true, then we can just swap the values. The question does not change, right? Then we know if that we can do it in 2 operations, right? We can do it in 2 operations of second type. We can do it in 2 operations. We can do it in 2C basically, right? But what if we wanted to do, what if we tried to do in one operation, like 1C plus some value, of that first operation, increase or decrease of Z. Okay. So what if we want to do in 1C? So the second operation we use only once, right? Because it might have a high cost. What if C was like 10 to the power 9? Then using this operation twice will be very costly. And if we found some value of Z such that it can be done in one shot, it would be nice, right? So we can try the second operation once, right? And find some nice value of Z and find a good value of Z. Okay. Right. And if you see the example, there's an example like 9342. Okay. So the example 9342 is a good example of this case. So example 9342. Now here you can see that x is greater than y. So we'll just swap both the x and y. Okay. Because it doesn't matter. We just need them to be equal. Right. So for convenience, I'm swapping both x and y. Now, if you observe that if we use z as 3, okay. So if we use one operation to make 4 into 3, so now new value of z will become 3. Okay. Then what we can do is we can use LCM of a and z and GCD of not a and z, x and z, and GCD of y and z. Okay. So GCD of y and z. And what happens? This is equal to LCM of 3 and 3, and this is equal to GCD of 9 and 3. Right. And then what happens? Both the values become 3. Right. So we took one step on z, and then in one shot we made it 3. Right. So instead of taking 2, so if we did 2 operations like the LCM and GCD where I described 2C cost here, 2C is 4. 2C equals 4, but here we did it in only cost C. So total cost, minimum cost is 3. Right. Minimum cost is 3. So this is equal to 2 plus cost to take z from 4 to 3. Okay. Right. All right. So now how do we figure out what values of z will satisfy? Okay. So basically our approach will be like this. We take the value of z from z to z dash. Okay. Then we know that x is less than y, right? So therefore we need to do LCM operation on x and GCD operation on y. Why is that? Because GCD will always make it smaller and LCM will always make it larger, right? So since we need them to be equal, we need to do LCM operation on x and GCD operation on y. Okay. So that should make sense, right? So then we will transform them into LCM of x and z dash. And we need this to be equal to GCD of y and z dash. Okay. And the reason we're doing LCM with x and GCD with y is because we said x is less than y, right? So we need to make x bigger and we need to make y smaller. So that's why we're taking LCM for x and GCD for y. Okay, that makes sense. Right. And now the second. So this much is clear. Any doubts? I hope there's no doubts so far. Yeah. Okay. So now one more thing to observe, and this is the key observation. So till now we made, I think, 3 observations, right? The first observation was that LCM and GCD, so 2 operations 2C will satisfy. If x equal to y, the answer will be 0. And if x is not equal to y, either we do it in 2C or otherwise we try 1C and we try this approach. Okay. So now this will be our key observation here, and let's see what it is. So given this equation, we can write the following key observation. Okay. And the key observation is GCD of y and z dash. Okay. GCD of y and z dash is a factor of y, right? Because that's what it means. Greatest common factor or greatest common device. So GCD of y and z dash, it will be a factor of y, correct? But we also have that LCM of x and z dash is equal to that GCD, is equal to, but then LCM of this is equal to a factor of y. Okay, a factor of y. So what does this mean? Since z dash is a factor of LCM, right? Since z dash is a factor of LCM and LCM is equal to GCD, which is a factor of y, right? So that means what happens is basically z dash is a factor of y, right? This is our conclusion, that z dash must be a factor of y, for this statement to be true. Like for this to be possible, z dash must be a factor of y. Like if this is true, then this must also be true that z dash is a factor of y. Okay. And now the problem is basically done. Since we can find all the factors of a number, right? We can find all the factors of a number, find all factors of y in square root time, right? Big O of square root of y and try it as a value for z dash. Try it as a value for z dash. Okay. So if this condition holds that LCM of x z dash equals GCD of y z dash, then our answer will become minimum of the current value of answer plus z minus z dash. So that's the cost to change z to z dash plus c, right? And obviously the original value of answer will be 2c, right? So the initial value of answer is 2c. C at start, right? And then we do this for all the factors of y. Okay. So what is our final time complexity? The time complexity of this approach is big O of square root of y to go through all the factors of y. Let's have a quick look at the code to make this clear what's going on. Okay. We have x, y, z, and c. We take in the values of x, y, z, and c. If x and y are equal, then our answer is simply 0. So we can print that and continue to the next test case. Okay. Otherwise, if x is greater than y, we're swapping. This is just to ensure that x is smaller than y, right? Like that is an assumption we made. Now our answer is 2c. Okay. So our answer is 2c because we know that we can do it in 2 operations. Now for all the factors of y, so we'll run I from 1 to y. And if y does not divide, then it's not a factor. So we continue. Otherwise, we know that I is a factor and y divided by I is a factor, right? This is how we find all factors. So this should be known if you have studied any number theory. Then we check if LCM of x and I is equal to GCD of y and I. In that case, the answer becomes minimum of answer plus c plus absolute value of z minus I. So that's the c plus z minus the dash that we described. Similarly, we'll try by the factor y divided by I. So we'll try for y divided by I as well. And if either work, like it'll update the answer, and then we can simply print the minimum answer. So what is the time complexity of this? It is big O of root y, or since y is defined as maximum of x and y, we can write it as big O of root max xy. Right, so we're making sure that y is the maximum. Okay. Hope that makes sense, guys. Any doubts? You can add it, ask it on the chat. Otherwise, we'll move to question 4. Okay. And question 4 also was, I think, easy only. Like once you read the question, it was easy itself. Once you understood the question, like it took me some time to understand the question. But, fifth question was unusually hard this time. I think only 2 people solved it. So yeah. Any doubts, or should we move on? Okay, let's move on. Right. Consider a tree with n vertices, and vertex u has some value a of u written on it. We have the following definitions. For 2 vertices u and v, define P of u and v to be the set of vertices on the unique path from u to v. Okay, so P of u to v is the vertices on the unique path. Define minimum of u and v to be the minimum value of these values, which are a of w, across all of the values in the path, right? So basically, we have a tree which goes something like this. Let's draw the tree. And let's say there are some values on the tree. It's a 3, 5, 4, 2, 1, 6, 7. Okay. And then if we take some path, let's say this is the path. Okay. Then what did they say? They said mn of u and v. So mn of this node, let's call this node 1 and node 2. So mn of node 1 and node 2 is the minimum of the values in the path. So the values in the path are 2, 4, and 5, right? So the minimum will be 2. So basically, it's the minimum value in the path between these two nodes. S equals MNUV for all nodes U and V. So S is the set of all path minimums of the tree. So across all paths, it is the set of the minimums in the tree. Okay. Then we define score of A as the smallest positive integer that doesn't appear in S. So I think the question, like explanation, is very complicated, but the question itself is not so complicated. So bear with it. Okay. So score is the basically smallest in positive integer. Obviously, negative integer cannot be there because there are no negative values. So we'll just write smallest integer. That is not a path minimum. That is not minimum of any path. That's what it basically means. Score is the smallest integer, which is not the minimum of any path. Okay. Score is the smallest integer, which is not the minimum of any path. That's what is the meaning of score. Okay. Yeah. And when considering paths with at least length 2, right? Because paths of length 1 doesn't make any sense in this context. So when we're considering paths of at least length, okay. Now what is the question itself? We are given the tree, okay. We are given a tree of n vertices array A, and we're given the array A. Each element of A is in the range 0 to n, okay, and it is guaranteed that non-zero elements are distinct. We should replace every 0 with an integer in 1 to n, and the elements of A must remain distinct. So the final array should be a permutation. Compute the minimum value of score that you can attain. Okay, let's unpack this and what this means. So basically, we are given the tree. We are given the tree. Also, we are given the values of the nodes, right? We are given array A, which is a permutation, which has to be a permutation. But basically it has some missing values, right? Basically it has but it has some missing values which are marked as 0. Missing values marked as 0, right? So we can fill them in any way as long as it remains a permutation, right? And we need to fill the missing values in such a way that the score is minimized. Okay. So basically, we need to find the minimum value of score. Find minimum value of score. Okay. So this is the whole question. It's a bit complicated question, I can say, but once you understand the statement, it's not that hard. So score is the smallest integer that is not the minimum of any path. We are given the tree and we are given array A, which is the values, which is a permutation, but it has some missing values which are 0. And we have to find the minimum value of score that we can make. Okay. So how do we approach this? Okay. So let's first simplify the problem. All right. So what if all the scores were given? Okay. So what if all values of A of I were given, right? That's a permutation. We know that A of I has to be a permutation. All the values need to be distinct and between 1 and n. Okay. So we're assuming that 0 is not there, right? Like there's an example in which 0 is not there. This example, 0 means we can replace it with any value we want as long as it remains a permutation. But here is an example where 0 is not there. So all the values are given. Okay. So therefore we have some tree. We already have some tree. And we simply need to compute the first value of score which does not occur in this tree. Okay. So we need to compute the first value of score which does not occur in this tree. Okay. So let me just draw some tree and see what is the first value of score which does not occur. Right. Now, if the score does not occur in a tree, what does that mean? Right. So let's say my current value is 5 and my adjacent values are 6, 3, 2. Okay. So let's say I'm starting at this node and I'm going to consider all the paths starting at this node. Consider all paths starting at this node. This node. Right. Now, since there is an edge from 5 to 6, okay, and here 6 is the larger value and 5 is the smaller value. So then the path from 5 to 6, right? The path from 5 to 6, the minimum value is already 5, right? The minimum value is already 5, right? So no matter whatever the minimum value becomes later, like even if you make a length 3 path and this value was 2, right? So we get a length 3 path like this. In this, the minimum value becomes 2. But the thing is, the minimum value has already been fixed because in this edge, 5 and 6, 5 is the smaller number, right? So 5 becomes a possible path minimum, right? So 5 has become a possible path minimum here. 5 has become a possible path minimum. Right. So for some value x to never be a path minimum, and this is our key intuition which will help us throughout the whole problem. So definitely pay attention to this. For some value x to never be a path minimum, all adjacent vertices should have some value less than x. Okay. And what do I mean by this? Let's take 2 examples. Here, let's say there is a node and it has a value of 5. Okay. And here, let's say there's a node, it also has a value of 5. Okay. Now, let's say my adjacent nodes have value 1, 2, 3, 4. And here, my adjacent nodes have value 1, 2, 3, 6. Okay. Now, in this case, in the first case, all these nodes are lesser than 5, right? So obviously, we can't have a path of size 1 itself. And if we have a path of size 2, Well, any path going through 5, right? Even if the tree is like this and there are other nodes, any path going through 5, it will go through either 1, or it will go through 2, or 3, or 4, right? So basically, always the path minimum will become less than 5, right? Path minimum will become 1, or the path minimum will become 2, or the path minimum will become 3, or the path minimum will become 4, right? Because any path will go through these. So that's why this condition is there. For some value x to never become a path minimum, all of the adjacent vertices should have some value less than x. Now here, because 5 and 6 is greater than 5, right? So now 5 becomes a possible path minimum. 5 becomes a possible path minimum. All right. So yeah, this is the key observation, key intuition, whatever you want to call it. Key intuition, right? For some value x to never be a path minimum, all adjacent vertices must have some value less than x. Okay, so this is our key observation. Now let us consider the actual tree. Okay, now consider the actual tree. And we will do this for each node. Okay, so we don't need to consider paths itself. We just need to consider edges. For each node, we just need to consider the adjacent edges. We just need to consider adjacent edges for each node. Okay, so for each node, one by one, we'll consider all its adjacent edges. Okay, so here is my node. And let's say it has some edges. Okay, now let's say the node already has some value. Okay, so let's say the node already has some value, which is a of I. All right, and let's say some of these nodes have values and some don't. Like let's say this one is or let's just give them actual values so it makes sense. So let's say the node has already given a value of 5, right? So it's possible that the value is already given. Like see here, there are some zeros and non-zeros. So some values are already there. Like for example, 3 is already there. So let's say this node already has a value of 5. And let's say this value is 7. This value is 8. Sorry, let's say this value is 1. This value is 3. And let's make the node's value 7. Okay. So this value is 1, 3, and this value is 4. These two values are set to 0. Okay. These two values are set to 0. Now, what condition I need to satisfy to make my score equal to 7? Right? What condition I need to satisfy to make my score less than equal to 7? I want to find the minimum score, right? So to make my score less than equal to 7, what I can do is a valid missing element is like for some value x to never be a path minimum, right? So we want 7 to never be a path minimum. So we want all its adjacent vertices to have value less than x, right? So observe that here the value is less than x, right? Here the value is less than x, here the value is less than x, and here the value is less than x. Now for these two, we can make choices. So we will put the smallest missing values here. Okay. So we can put the smallest missing values here. So let's say if in the tree values 2 and 5 were missing. Okay. So we'll put 2 and 5. Then we will check if this 2 is also less than 7 and 5 is less than 7. Since both are less than 7, we can say that our score, the new minimum value of our missing score, or whatever you want to call it, basically the minimum value of score that is not a path minimum is 7, right? We can update our score to 7. Basically, if this condition holds, we can say that score equals or answer equals minimum of answer and 7. Okay. So what do? We fill the missing values with the smallest missing values possible. And then we check if the middle node is greater than all the other nodes. If the middle node is greater than all the other nodes, then there is no path with this one as a minimum. So we can update our answer to be minimum of answer and 7, basically. Right. And what if the middle node itself did not have a value? Okay, so what if the middle node itself was a 0, right? The middle node was a 0, and some of its adjacent nodes have values and some of its adjacent nodes are zeros. Okay. So let's say there is a set called missing, right? And this is the set of the permutation elements which are missing. Let's say 3, 5, 6 are missing right now. Okay. And let's say this is a 0, this is a 0, this is a 1, and this is a 2. Okay. So what do we do for such a node? Well, first the outside nodes will do the same thing. We'll put the minimum missing value for them. Okay. So the minimum missing value is first 3. So here we'll put a 3, right? And now here the minimum missing value is 5. So we'll put a 5, right? And then the minimum missing value is 6. So for the central node, we'll put 6. Okay. And now we can see that 6 is greater than 5, right? And 6 is greater than 3. 6 is greater than 1. 6 is greater than 2. So we can update our new answer to be 6. So our answer can become 6, because it is possible to construct a tree such that, 6 is the minimum path value that does not appear. 6 is the minimum path value, but that does not. Okay. Now let us take a more interesting example where all are zeros. Okay. So this is our case 1. This is our case 2. Basically, the only difference is that the central node is 0, right? And what happens when the central node is 0? Now let us again write our missing values. So let's say this is 9. Okay. Now let's say our missing values are, missing means the ones which have not already appeared in the permutation A. So like if you observe here in 3002, 1 and 4 are missing. And then in 400502, 1, 3, 4, 1, 3, and 6 are missing, right? So those are the missing values what I'm talking about. So we can store the missing values in a set. Okay. So now let's say the missing values are 2, 3, 4, 5, 6, 11, 12, 13, 14. Okay. So let's say these are the missing values, right? Now what I can do is I will fill the again smallest missing value here. So I'll put 2. Then here I'll fill the smallest missing value, right? 3. But what happens is I can't put a 4 over here because 4 is less than 9, right? 4 is less than 9. So the minimum path value over here, becomes 4. So that's not a valid, minimum missing score, right? Because this path has minimum as 4. We don't want this path to have minimum as 4, correct? So that's why 4 is not valid. Similarly, 5 is not valid here. 6 is not valid here, so on. In fact, the number which is put here should be greater than 9. Okay. The number which is put here should be greater than 9. Otherwise, it won't be a valid number to put at this node, right? So what we can do is in the set of missing values, we will look for upper bound of max of all the adjacent nodes. Okay. So we will look for the first value greater than 9. Okay. And that is 11, right? So the first value greater than 9 or the upper bound of 9, upper bound of values, upper bound of max of adjacent values. Okay. And the first value is 11. So now if we put 11 over here, we can see that 11 is greater than 3, 11 is greater than 2, 11 is greater than 1, 11 is greater than 9. So it's greater than all of these. So it's a valid new minimum, right? So we can say answer is the minimum of answer at 11. Okay, so that's how to approach the problem. Let me quickly summarize. Take input, right? And of the tree, store in adjacency list, right? Store in adjacency list. And obviously take the input of the values. So take input of AFI, right? And store the missing values in a set. So store the missing values in a set. Missing values in a set. Okay. Now for each node in the tree. So for each node means for I from 1 to n, each node in the tree, we'll make a vector of adjacent values. Okay, vector of adjacent values. And what this will be, it will store all adjacent values. If an adjacent value is 0, if adjacent value is 0, it will store the minimum value. It will store minimum next missing value, right? So the same thing which we did there. It will store the minimum next missing value. Basically, here it's a 0, right? So we'll store the smallest value possible, 2. Now here it's a 0, and 2 and 5 were available missing values. So since 2 is already used, we'll store 5 for this node. Okay. So we will store all adjacent values. If it's 0, store the minimum next missing value, right? So we'll have an iterator through the set of missing values. We'll add the next value in the set and we'll move our iterator forwards. Okay. Then what do we need to do? What we can do is, now if center node, or if node I, so if this is not 0, right? Then we can check if V of I is larger than all adjacent values, right? If it is larger, then we can update our answer. So then we can say that our answer can be updated with minimum of answer and V of I. Okay. And this is if V of I is not 0. Now, if V of I is 0, then we can put some value here as well, right? And what value can we put? The value we can put will simply be upper bound in our missing set. So missing dot upper bound. And what will be the upper bound of? Max element of adjacent values, right? So the first value in the missing set, which is greater than the maximum of adjacent values. Now, if this is equal to, if no such element, continue, right? Let's call this X. If no such X, then you can continue. Otherwise, answer will be the minimum of answer and X again, right? Because we set that as central node. And since we specifically chose that central node, that it's bigger than all the others, so that's also a valid update, right? So in this case, this will be our X. This is the node we binary searched, or we did upper bound and found that it is greater than 9, right? Which was the maximum adjacent. Okay, so basically what we're doing is, for all the adjacent nodes, we're greedily filling the smallest value they can have. And for the middle node, if the value is already there, we simply check it. Otherwise, we find the first value, smallest value, larger than, which is bigger than all the adjacent nodes, right? And that way we are finding the, minimum value of missing path length, or what can you say, minimum value of score. And what was score? Score is basically the smallest min of all paths of length greater than equal to 2, right? So this was the question. And basically that's how we're approaching it. We want to minimize this. So each time we are assuming that all my adjacent nodes are smaller than me, and I'm checking if that is possible to fill it that way. And if the central node itself is not filled, then I will fill it in such a way that it is larger than all the adjacent nodes. And then that will be a new score which does not occur in our set of minimum path values, right? So let's have a quick look at the code for this, how to implement this. Okay, so first thing we do is we take our input as n. We make a set of missing values which has the values from 1 to n. Then we take in our vector or array, which is our permutation. And if it is, if the value which we have taken in is there in missing, right? So we erase that value. So basically we want only the missing values. So the values which are already there, we'll erase those, right? Okay. Then we make our adjacency list and we take input of our tree, correct? Then our answer initially is n, because obviously n will be the maximum possible answer. No path will ever have n, since any path will always be less than n, right? So that's why any path minimum is less than n. So that's why we're setting answer equal to n, and then we'll take minimum later on. Now, for each node from I equals 0 to I equals n, we are creating this vector of adjacent values, right? And then what we're doing is, if the adjacent value is there, then we simply push back into this vector. Otherwise, we push back the smallest value in our set which we have not added. So for example, this is the first value of our set, right? Missing dot begin. So if this is a missing value, we will add the smallest value of missing, and then we'll increase our iterator, right? So this will make sure that what I described happens, that the empty values get filled with the smallest possible values that we can put at that position, right? And we're doing this separately for each node. Keep that in mind. So these adjacent values are completed separately for this one. Now, if the central node itself has a value, so if the central node already has a value, then we simply need that the central node should be larger than the max of all in the adjacent values, right? So we take max element of adjacent values. And if the central node is larger than that, then we can update the answer. Now, if the central node itself is not set, we need to set the central node in such a way that the answer is possible. So we'll set it to the first value in missing, which is greater than the max element. Okay. So we set to missing dot upper bound max element of adjacent values dot begin dot end, right? So basically, we set it to the first value not present in the, which is missing and which is not in the adjacents, right? Which is bigger than the adjacent values. Now, if there is no such value, so if this becomes missing dot end, we can simply continue, it's not possible. Otherwise, the answer becomes minimum of answer and this value, so star it. Okay. We dereference the iterator over here. All right. And then we can simply print the answer once we are done. What is the time complexity of this approach? So since we are using the upper bound function, so if you observe, this only happens n plus m times, right? So this loop goes n times, and this loop will go m times, where m is the number of edges. And in a tree, the number of edges is also n itself. So it's going to happen big O of n times. And then in each of these n iterations, we might use the upper bound function, correct? We might use the upper bound function over here. So the final time complexity will be big O of n log n, right? Because the upper bound function is doing a binary search on our set. That's why it's big O of n log. Similarly, to insert in the set itself, here it's n log n. So yeah, that's why inserting and removal from set. No, there's no removal, but yeah, insertion into set and doing upper bound on set, both are log n operations. That's why the overall time complexity is big O of n log n. All right. So I hope this was understandable. Can you explain the third case again? Okay, I'll just quickly do that. Aditya. Okay. Which is the third case again? I think you mean this case, right? So basically, when the middle value is not set, right? When the middle value is not set, this is a question mark. The middle value is not set. We want it to be larger than all the adjacent values. We want it to be larger than all adjacent values, because otherwise it will be smaller than adjacent value, and then they'll form a path with this one as minimum, right? So we want it to be larger than all adjacent values, right? And the second thing we want is it should be as small as possible while keeping this in check, right? As small as possible, because we're trying to minimize the answer, right? So it should be as small as possible, but it should be larger than all the adjacent values, right? So that's why we're setting the adjacent values to the smallest possible. Like we set this to 2 and 3, right? The minimum, the missing values in this case were 2, 3, 4, 5, 6, 11, 12, 13, 14. That's why we set it to the two smallest, 2 and 3. Now the middle one, we take max of 2, 3, 1, and 9, which is 9, right? So the first element which is missing, which is greater than 9, right? It is 11, right? So here 12, 13 and all will work, but they won't give us minimum answer, right? So that's why we put 11 over here, and we put 11 over here, and we update our answer with minimum of answer in 11. And this is because we know that if we put a 11 over here and 3 to 9, then none of the paths will include a score of 11, right? None of the paths will have minimum of 11, because minimum of 11 and 3 is 3, Minimum of 11 and 2 is 2. 11 and 1 is 1. 11 and 9 is 9. Right? If we put 5 instead, the minimum of 5 and 9 would be 5. And so it would not be excluded from our set of minimums. Right? So that's why we're using 11, which is the smallest number greater than everything adjacent. So I hope that that answered your doubt. If there's any other doubts, you can ask it now. Otherwise, we'll end the session here. All right, then. Thank you everyone for tuning in, and thank you for everyone who's going to watch this on YouTube later as well. If you're watching on YouTube, then do check out TLE's self-paced course, which is out right now. Thank you, and see you next time.